Hello students, welcome to lecture 5 of atomic structure. In previous class, we discussed about wave nature of electromagnetic radiation. Now we are going to discuss about particle nature of electromagnetic radiation. The diffraction and interference can be explained by the wave nature of electromagnetic radiation. The diffraction and interference can be explained by the wave nature of the electromagnetic radiation. But the nature of emission of radiation from the hot body, nature of emission of radiation from hot bodies, it is called black body radiation. Black body radiation. And ejection of electrons from metal surface when radiation strike the metal is called photoelectric effect. And heat capacity of solid as temperature and line spectrum of atoms are not explained by the wave nature of electromagnetic radiation. So these observations are not explained by the wave nature of electromagnetic radiation. Next one, particle nature of electromagnetic radiation, Planck quantum theory and black body radiation. Let us discuss the key points of Planck quantum theory. Max Planck introduced the quantum theory in 1900. Max Planck introduced the quantum theory in 1900. The emission of radiation is due to vibrations or rotations of charged particles. Emission of radiation is due to the vibrations or rotations of charged particles, electrons. And the emission of radiation is not continuous. It is pockets of energy called quanta. The emission of radiation is not continuous. It is packets of energy called quanta. And the energy of each quanta is directly proportional to its frequency. The energy of each quanta is directly proportional to frequency, directly proportional to its frequency mu. Then here we are taking that constant, Planck's constant. So E is equal to h nu, and here mu is equal to frequency and h is equal to Planck's constant. And its value 6.0 626 into 10 to the power of minus 27 erg into second, or 6.626 into 10 to the power of minus 34 joule into second. And a body can emit or observe one quantum of energy or whole number of quantum of energy. A body can emit or observe either one quanta of energy or whole number of quantum of energy. So E is equal to NH nu, and here N is equal to whole numbers 1, 2, 3 and so on. Then we can write E is equal to, if N is equal to 1, 1 H nu, if N is equal to 2, 2 H nu, if N is equal to 3, 3 H nu and so on. And Planck's quantum theory successfully explained the black body radiation. A black body is a perfect observer and also a perfect emitter. Of radiation. Planck's quantum theory successfully explained the black body radiation. A black body is a perfect observer and also a perfect emitter of radiation. And the black body is a hollow metallic sphere inside with platinum black. It is a hollow metallic sphere inside with platinum black. And having a small hole in its wall. Let me draw that black body. So black body is a hollow metallic sphere inside with platinum. So this is the black body and it is a hollow, and here it is a platinum black coating. So black body is a hollow metallic sphere inside with platinum black and having a small hole in its wall. And the radiation emitted by black body when passed through a prism produces a spectrum with different wavelengths. The radiation emitted by black body when passed through a prism and produce a spectrum with different wavelengths. Let me draw the graph. This is the graph between intensity and wavelength. On y-axis we are taking the intensity, On x-axis we are taking the wavelength, and this is the peak at higher temperature, and this is the peak at lower temperature. So at a given temperature, the intensity of radiation gradually increases as wavelength increases and then decreases. So at a given temperature, the intensity of radiation gradually increases as wavelength increases and then decreases. And as temperature increases, the peak of curve shifts towards the lower wavelength. And this is the peak at lower temperature, and this is the peak at higher temperature. So at lower temperature, the peak appear at higher wavelength, and at higher temperature the peak appear at lower wavelength. So as the temperature increases, peak of the curve shifts towards the lower wavelength. With this theory, Planck explained the distribution of intensity of radiation from black body as a function of frequency and wavelength at different temperatures. So this is about Planck's quantum theory and black body radiation. Next one, photoelectric effect, and this is the equipment for studying the photoelectric effect. So here, this is the metal with potassium or rubidium or cesium. So these are the metals, and here it is a vacuum chamber, and this one is the battery, and this is the ammeter, and this is the detector, and this is the light. When the light fall on that metal, the electrons are ejected from the metal. When a beam of light with a suitable wavelength is fall on that surface of the metal, then electrons are emitted from the metal. So these are the electrons which are ejected from the metal. So here, when a beam of light with a suitable wavelength is fall on that surface of the metal, so this light is fall on that metal, then electrons are emitted from that metal, and this phenomenon is known as photoelectric effect. And photoelectric effect observed or performed by the Hertz scientist, and it explained by the Einstein. And electrons are ejected from the metal surface as soon as beam of light strike on the metal surface. That means there is no time gap between the striking light and ejection of electrons. In the sense, these two are appear simultaneously. So here, striking of light and ejection of electrons are occur simultaneously. There is no time gap between the striking of the light and ejection of the electrons. And number of electrons ejected is directly proportional to the intensity of light or brightness of light. Here, ejection of electrons is directly proportional to intensity intensity of light or brightness of light. Means more intensity, more electrons are ejected. And every metal has a minimum frequency called threshold frequency. Every metal has a minimum frequency called threshold frequency. Threshold frequency is represented by mu naught. And photoelectric effect is not observed if incident light frequency is less than the threshold frequency. The incident light frequency represented by mu and threshold frequency is represented by mu naught. So here the photoelectric effect is not observed if incident light frequency is less than the threshold frequency. So in this case, the photoelectric effect is not observed. And photoelectric effect is observed when incident light frequency is more than the threshold frequency. The incident light frequency is more than the threshold frequency. In this case only the photoelectric effect will be observed. Let me take some examples here. The threshold frequency mu naught for potassium metal is mu naught is equal to 5 into 10 to the power of 14 hertz. And electrons are not ejected by using the red light because the red light frequency is mu is equal to 4.3 to 4.6 into 10 to the power of 14 hertz. This is the incident light frequency and this one is the threshold frequency. So the incident light frequency is less than the threshold frequency. Then electrons are not ejected. This is the red light frequency. But electrons are ejected by using the yellow light. The yellow light frequency, mu is equal to 5.1 to 5.2 into 10 to the power of 14 hertz. And the threshold frequency is mu naught is equal to 5 into 10 to the power of 14 hertz. So here the incident light frequency is more than the threshold frequency. So in this case the electrons will be ejected. So using the red light, electrons not ejected, but using the yellow light, electrons are ejected. And kinetic energy of ejected electron. Kinetic energy of ejected electron is h nu, and the minimum energy required to eject the electron is h mu naught. Then the difference in energy is h nu minus h mu naught transferred as a kinetic energy. So h nu minus h mu naught is equal to kinetic energy Ke. So kinetic energy of ejected electron h nu is equal to, if it is come to this side, plus h mu naught. So h mu naught plus ke, then h nu is equal to h mu naught plus kinetic energy of me mu square. So here me is the electron mass. So h nu is equal to h mu naught plus of me mu square. So this is about photoelectric effect.